Let's talk about how we solve a statically indeterminate system. So if we want to solve a statically indeterminate system in strength of materials that is axially loaded, we need two things to be true. We need to make sure that we are working in the linear elastic region so that our relationships like Hooke's law hold true, and St. Venant's principle is also not affecting anything. We want our relationships of sigma is F over A to hold true. We want to be in the linear elastic region where we have our stress over strain. So that way our axial load equation that we've been working with, the force times length over area times modulus of elasticity, all of these hold true. That's what we need. So we need the loading to be linearly related to the stress and the displacement. And we also need to make sure that our external loading doesn't significantly change the geometry in any way, right? So with St. Venant's principle, we said, oh, well, maybe the end part, it's going through a little bit of deformation at the top, and then it stays pretty much normal shape everywhere else, right? So we don't want this to be like a tube of Play-Doh where you kind of squish it and the geometry all changes from the load of your hand squishing it. We want the geometry to stay intact so that way we can make sure that things like the area and the length that we're working with are going to be about right. Right, so those are the two assumptions that we need. Linear elastic, and that the loading is not changing the geometry. Right? Constant geometry, linearly elastic. Those are the assumptions that we're going to make going forward. So now that we have that out of the way, we're going to talk about two different methods you can use to solve these equations. So in this video, we're going to talk about this force method, or you might also hear it called the flexibility method. I often think of it as like the superposition method because we use superposition to solve it. So what is superposition, right? Superposition just means that we can add the stress or displacement caused by each individual load separately. So this concept of superposition is, let's say we have our beam here, it's attached to a wall, and let's say there's a force P1 on it and another force P2 on it. All superposition says is that whatever this displacement is here caused by P1 and P2, I'll call this delta, whatever this is going to be the same as whatever the displacement is of this beam caused by P1. So P1 might cause it to move out by about that much. That would be our displacement 1, plus whatever displacement P2 causes. So each load separately, right? P2 would cause it to move inwards, right? By compression, by D2. So all this says is that delta is equal to the displacement D1 plus the displacement D2. Of course, this D2 would be a negative since it's moving inwards, but you kind of see the point there. All it is it says is each load component separately, we can sum the stresses or the displacements of those individually. Right? So we can sum these individual displacements caused by each individual load, and that gives us the same as the overall displacement. So it's a really handy tool we can use, right? We used something similar when we were talking about axial load. So this idea of superposition is how we're going to tackle this. So I'm going to give you a basic outline of steps that we're going to follow for this force method or this flexibility method, whatever you want to call it. I'll give you an outline of steps of how we'll do it, but it'll make a little more sense as we work through an example. So our basic steps, all this procedure for analysis, right? Anytime you're given something statically indeterminate. Generally first degree is going to be easiest. So statically determinate. One, draw your free body diagram, just because I like them. Now, draw your free body diagram and make sure that your thing is actually statically indeterminate, because you may draw it and you may find that it is or it isn't, right? So if it's statically determinate, just use statics. And if it's not, say, maybe you have two unknowns, but you can only use one equation, then it's statically indeterminate to the first degree. And we'll keep on with this procedure, right? So draw your free body diagram, make sure you're statically indeterminate. And then what we're going to do is we're going to redraw the problem as if one of the reactions is not there. So you're going to redraw problem, not the free body diagram, the actual problem diagram. Problem as if one reaction is not there. And so what this will allow you to do is to break that out and then use superposition to put back in that reaction that is not there. So you're going to draw it out, draw the displacement, draw displacement, right? And then once you draw that problem and draw how its displacement would work, you're going to replace, use superposition. Use superposition for reaction / displacement. So whatever that displacement is, go ahead and use superposition. You got rid of one reaction, you did that displacement, now you're putting the reaction back in, you're doing that displacement so that we can add them together to find the displacement overall. Right, so 4 is going to be find a displacement relationship between those displacements that we found. Usually it'll just be adding them together, but there may be more complicated geometries going on. You're going to find the displacement relationships, and then you're going to substitute in our axial load equation that we've been working with. Right, so we call this a load displacement relationship, but I'm just going to write D equals FL over AE, right? We're going to create this relationship between the load, our force here, and the displacement. So once we substitute that in, we should now have enough equations with our equilibrium equations. Use this in conjunction with equilibrium equations from statics. Equilibrium equations from statics to solve reaction. So really it's this step here, step 5. Step 5 is giving us that relationship between load and displacement that will give us our reaction that we're missing, or our equation that we're missing, right? So if we had two unknowns and one equation, this is what's really giving us that extra equation, right? Finding a displacement relationship and then substituting this in so that way we can get the displacement to relate to the load. That's how we come up with this extra equation that we need to solve. And this, I know this seems a little abstract right now, but as we work through a problem, it'll make a little bit more sense. And if you don't like this method of problem solving, we'll do another method of problem solving. They'll both get you to the same place. It just depends on which method you kind of like more. So try them both out and see which one you like more. This is the flexibility method, and we're going to try an example. So this example asks us to find the reactions at A and B given this little diagram on the left. So we have this tube, it looks like, that is axially loaded with 500 newtons that is fixed between two walls. So it's stuck against the wall at A and stuck against the wall at B, and then there's a 500 Newton load being applied to not quite the center, it's 2 meters from A and 3 meters from B. So what we're going to do is we're going to go through those steps that we had looked at, right? We know it's statically indeterminate, mostly because it's stuck between two walls. But if we draw the free body diagram for this, I kind of just take the walls out. I'm going to say I've got that reaction from the wall at B. I've got a reaction from the wall at A. And then there's that 500 Newton applied load. So we can tell it's statically indeterminate, right? We have two unknowns, one equation, right, which is our sum of forces in the y direction. Again, we can't use a moment here, and we can't use our sum of forces in the x direction. So the only equation we have left from our statics knowledge is sum of forces in the y direction. So that makes this statically indeterminate to the first degree. So now that we have that out of the way, we're going to use our superposition method to determine the relationship between the displacement for this given geometry. The displacement relationships are going to be different for every single problem that you do. It'll be the hardest part of figuring out these problems, is figuring out how the displacement is actually changing for each individual problem that you're given. So in this one, as we break this down, our first step was to imagine one of the reactions is not even there, right? So in this, it asks us to redraw this problem without one of the walls being there, right? Without that reaction at B being there. You could also do it at A, but for the sake of argument, I'm just going to do this for B. So our first step is, all right, what does this look like if B isn't there? So I've got a 500 Newton load and B is not there. This is what my problem looks like. So my displacement, this here, I'm going to call this D from my load. I'll call it D sub P. D from the load here. So what I'm going to do is take this knowledge and then take my knowledge of superposition to say, okay, if this is the case when B is not there, then when B is there, right, the loading, when force B is applied here by superposition, this delta B. These two together must give us the overall change in displacement. And we know what the overall change in displacement is. Because of its original geometry here, the original displacement has to be 0, right? It's stuck between two walls. It's not actually moving anywhere. It physically can't. So what we're going to end up with is a displacement that's 0, but a displacement that by superposition is going to equal dp minus db. And this minus db is just because this db is moving inwards. It's a negative displacement. So this might be kind of intuitive, right? Whatever distance that P moves it out, B has to move it back in, because physically, like, it cannot move. It is stuck between two walls. There is absolutely no room for displacement. No displacement is possible under this geometry. The displacement must be 0. So this is this superposition method, this flexibility method that says, okay, look at it as if it's not there, then look at the reaction that has to be caused due to the geometry, and you'll see a lot of different geometries, right? So they may not be as simple as displacement equals 0. They may not always be displacement equals 0. But for this specific case, this example, what we can get from this superposition is this equation here. 0 equals dp minus db, or delta p has to equal delta b. So that's all fine and dandy, but what do we do with that, right? This is the hard part. This is the hardest part, getting this displacement relationship. The next step is to substitute in that axial load equation that we've been working with. Your axial load equation of NL, or force times length over area times modulus of elasticity. So we can go ahead and substitute that in for P and B. So P, that's our given load, times the length that that load is acting over, I'll call that LP, over area times modulus of elasticity. Now, you'll notice in the problem, we weren't actually given an area or a material that this thing was made of, a modulus of elasticity or anything. But that's going to be okay because our B and our P functions here, both of these have the same cross-sectional areas and the same moduluses of elasticity, which we're assuming just because it looks uniform all the way down. There's no indication that there's a change in material. There's no indication that there's a change in area. So we're going to assume that this is just a uniform rod. So we've got this over AE. And what is that? That's our FB coming from this diagram here. FB times the length B acts over area times modulus of elasticity. So as we multiply this out, our AE terms cancel. We don't actually need them. And what we get is 500 newtons, that's our P, times the length that P acts over. It's axially loaded. P is acting over this 2 meter area here from our axial load. So 500 times 2 meters equals FB times the length of FB. That overall length was 5 meters. Meaning that this actually gave us a direct solution for FB. We didn't have to do anything else. We can just plug that into our calculator and see that FB is 200 newtons. So that's one of our reactions. Like, that's done and solved. We have the reaction for B now, which was given to us from this load displacement, from this displacement geometry that we found. Now that we have FB, we can come back to our free body diagram that we made here at the beginning and write out our equilibrium equation. Sum of our y forces equals 0. So FA plus FB minus 500 equals 0. And we can sub in 200 for FB. So we find that our reaction FA is 300 newtons. And note that both of those I got positive answers for, which means I assumed the correct direction for each of these, right? FB is pushing up and FA is also pushing up. So pretty cool, right? Before, we never could have solved this problem just using statics. Now that we have these displacement relationships because of Hooke's law and the way we axially load things if we're working in the linear elastic region, we have all of these additional relationships that we can solve problems that were never possible for us to solve before just using our statics knowledge.